Somewhere in a cooled steel chamber colder than the empty space between stars, a machine is quietly rewriting the rules of intelligence itself. It has no eyes, no voice, and no ambition of its own. But inside it, particles are doing something that should be impossible. Existing in two states at once, whispering information to each other across distances that classical physics says shouldn't matter. And right now, in labs from Mountain View to Beijing, from Armonk to Zurich, engineers are trying to plug artificial intelligence directly into that strangeness. If they succeed, it has worked spectacularly, until it hasn't. Engineers are running into walls that money alone can't knock down. Training the largest AI models now consumes as much power as a mid-sized city. The improvements are getting more expensive for each incremental gain. And somewhere in the back rooms of Google, IBM, Microsoft, and a handful of Chinese state laboratories, a quiet question has been forming. What if the problem isn't the size of the model, but the nature of the computer running it? What if classical bits, simple ones and zeros, are simply the wrong material to build a truly intelligent machine? That question is where quantum machine learning begins. To understand why it matters, you have to understand what makes a quantum. Somewhere in a cooled steel chamber colder than the empty space between stars, a machine is quietly rewriting the rules of intelligence itself. It has no eyes, no voice, and no ambition of its own. But inside it, particles are doing something that should be impossible. Existing in two states at once, whispering information to each other across distances that classical physics says shouldn't matter. And right now, in labs from Mountain View to Beijing, from Armonk to Zurich, engineers are trying to plug artificial intelligence directly into that strangeness. If they succeed, the AI systems we know today, the chatbots, the recommendation engines, the image generators, will look as primitive as a calculator looks next to a supercomputer. This is the story of quantum machine learning, and whether you realize it or not, the outcome of this race may quietly decide who leads the next century. For the last decade, artificial intelligence has grown by brute force. Bigger models, more data, more electricity, more chips stacked into warehouses the size of small towns. It has worked spectacularly, until it hasn't. Engineers are running into walls that money alone can't knock down. Training the largest AI models now consumes as much power as a mid-sized city. The improvements are getting more expensive for each incremental gain. And somewhere in the back rooms of Google, IBM, Microsoft, and a handful of Chinese state laboratories, a quiet question has been forming. What if the problem isn't the size of the model, but the nature of the computer running it? What if classical bits, those simple ones and zeros, are simply the wrong material to build a truly intelligent machine? That question is where quantum machine learning begins. To understand why it matters, you have to understand what makes a quantum computer fundamentally different from the laptop or phone in your hand. A classical bit can be a 0 or a 1, nothing else, ever. A quantum bit, a qubit, can be a mixture of both at the same time, a hazy in-between state called superposition, until the moment you measure it. Two qubits can also become entangled, linked in such a way that changing one instantly affects the other, no matter how far apart they are. It sounds like science fiction. It isn't. It has been demonstrated again and again in laboratories around the world. And when you chain enough qubits together, something extraordinary happens. The amount of information they can represent doesn't grow steadily, it explodes exponentially. A system of just 50 well-behaved qubits can represent more possible states than there are atoms in your body. A system of a few hundred can represent more states than there are atoms in the observable universe. Now imagine feeding a machine learning algorithm into that landscape. Classical machine learning works by searching through enormous spaces of possibilities, from the space of all possible ways to draw a boundary between cats and dogs in a data set, the space of all possible molecular configurations, the space of all possible next words in a sentence. Classical computers search that space one step at a time, however cleverly. A quantum computer, in theory, can explore vast swaths of that space simultaneously, using interference patterns to amplify the right answers and cancel out the wrong ones. That is the promise sitting at the heart of quantum machine learning. Not just a faster version of the AI we already have, but potentially an entirely different kind of pattern recognition, one built on the actual physics of nature rather than an approximation of it. Computer in a very specific quantum format, and getting classical data into that format can itself take as long as just solving the problem classically in the first place. This is what researchers now call the data loading bottleneck, and it might be the single biggest obstacle standing between quantum machine learning's theoretical promises and its practical delivery. You can have the fastest engine in the world, but if it takes longer to load the fuel than to just walk to your destination, the speed doesn't matter. This is the tension sitting at the center of the entire carefully chosen physics and chemistry benchmarks, but haven't yet touched the kind of workloads that would make a bank, a hospital, or a social media company switch over their AI infrastructure. That gap between laboratory proof and boardroom deployment is exactly where billions of dollars in investment are currently being gambled, and exactly why nobody in this race is willing to blink first, because underneath the algorithms and the processors, there's a harder, colder strategic reality driving all of this money and ambition. Whoever masters quantum machine learning first doesn't just get a faster search engine or a slightly better chatbot. They get a potential edge in drug discovery, simulating molecular interactions that would take classical computers millennia to model accurately, possibly compressing a decade of pharmaceutical research into a fraction of the time. They get an edge in financial modeling, running risk simulations, and portfolio optimizations across possibility spaces too vast for any classical machine to fully explore. There are security strategies being written right now. So where does this actually leave quantum machine learning? Practically in the middle of 2026. It leaves it in an uncomfortable, thrilling place right at the hinge point between promise and proof. The hardware is improving faster than almost anyone predicted even 3 years ago, with error rates finally beginning to fall as machines scale up instead of the reverse. The software ecosystems, Qiskit, TensorFlow Quantum, PennyLane, and others, are maturing into genuinely usable tools rather than academic novelties, lowering the barrier for classical machine learning researchers to start. Experimenting with quantum subroutines without becoming physicists themselves. Hybrid quantum classical pipelines are quietly becoming standard practice in pharmaceutical and material science research, even if they haven't yet reshaped mainstream consumer AI. And the geopolitical stakes have turned what could have been a niche academic pursuit into one of the most heavily funded, most closely watched technology races on the planet, with tens of billions of dollars flowing into the sector, up dramatically from just a few years ago. But nobody serious in this field will tell you the outcome is decided. The barren plateau problem hasn't been solved. The data loading bottleneck hasn't been solved. Nobody has yet built a fault-tolerant, error-corrected quantum computer large enough to run these algorithms at a scale that would matter to an ordinary business, let alone an ordinary person. Every credible roadmap from every major company still points toward the end of this decade, not tomorrow, before the truly transformative machines arrive. What we're watching right now is the opening chapter, the equivalent of watching the first shaky, sputtering airplanes leave the ground at Kitty Hawk. Knowing that somewhere down the line, this technology will cross oceans, but not knowing exactly which design, which company, or which country's approach will get us there first. And that's what makes this moment worth paying attention to, more than the flashy demos and the billion-dollar funding rounds. We are living through the earliest days of a second kind of intelligence, not artificial in the sense of mimicking a human mind, but quantum in the sense of borrowing directly from the strange, counterintuitive rules that govern reality at its smallest scale. If it works the way its architects hope, quantum machine learning won't just make our AI systems faster, it could make them capable of understanding patterns in nature that classical computers, built on classical logic, may never be able to see at all. Patterns in how proteins fold, how materials behave, how diseases spread, how markets move. The question hanging over all of it isn't really whether quantum computers will eventually beat classical ones at certain kinds of learning. Most researchers now think that's a matter of when, not if. The real question is who gets there first, what they choose to do with that advantage. Once they have it, and whether the rest of us will even understand the world they build with it until we're already living in it. So keep watching this space, because the headlines you're seeing now, a new chip here, a record-breaking calculation there, or quiet tremors before something much bigger. If you want to keep following this race as it unfolds, stick around, subscribe. If you'd like more of these deep dives, and let me know in the comments which country or company you think crosses. Then there are quantum neural networks, which try to recreate the layered structure of a classical deep learning model, but using quantum circuits instead of matrix multiplications. Data gets encoded into the quantum state of a set of qubits, passed through layers of quantum gates that act something like the weights and activations in a normal neural network, and then measured. Several research groups, along with corporate labs at IBM and Google, have published early theoretical results suggesting specific, narrow problems where this quantum kernel trick provably outperforms anything classical. The catch? The Haro-Hasidim Lloyd algorithm, often just called the quantum algorithm for linear systems. An enormous amount of machine learning underneath all the buzzword Hess comes down to solving systems of linear equations, the math behind linear regression, the backbone calculations inside more complex models, the recommendation engines that decide what video autoplays next. In 2009, researchers showed that, under the right conditions, a quantum computer could solve certain massive linear systems exponentially faster than any classical method. It became one of the most cited results in the entire field, and also one of the most misunderstood, because those right conditions are extremely restrictive. The data has to already be loaded into the quantum